Hello friends, today in this session we are going to study what are the different types of organic reactions. So what are those types? The reactions are substitution reactions, next is our elimination reactions, third is addition reaction, rearrangement reaction, fifth is condensation reactions, sixth is isomerization reactions, 7 is polymerization reactions, 8 is pericyclic reactions. Reactions are also so many types. These are the somewhat main type of reactions, in which substitution reactions, elimination reactions, addition, rearrangement reactions are used in most of the organic reactions. First 4 reactions. So we will see the first 4 reactions in detail, and we will give the remaining reaction as one examples. Let us see which are those reactions. First is, what is substitution reactions? So in case of substitution reactions, what is actually, this is again it is 3 types. One is substitution by electrophile, SE, means when the reaction is when the organic reaction is substituted by the any electrophile, it is called as a substitution reaction. Next is substitution by the free radical. When it is substituted by the any free radical compounds, it is called as radicals, it is called substitution by free radicals. And when same organic reaction is substituted by the nucleophile, then it is called as substitution reactions by nucleophile. Then again by nucleophile also there are different type of reactions. One is SN1, next is SN2. SN2 is also called as the concentrated reaction. Concentrated reaction means the reaction which takes place in one step or single step. Second is SN2 prime. SN2 prime is the allylic rearrangement reactions. Then your aromatic nucleophilic substitutions. So it is again 2 types. One is addition elimination, and the second is elimination addition via Benzyne mechanism. So already I have given this session over aromatic nucleophilic substitution reactions via Benzyne mechanisms, and see the heading of Benzyne reactions. Then next is SNI. SNI is internal nucleophilic substitution reactions. And the last one is the neighboring group participation. So neighboring group participation is another type of substitution reaction. So all these will study details. Now next is elimination reaction. Elimination reaction is E1 reaction. Next is E2 reactions, and next is your E1CB reactions. E1 by conjugate base, and again next is alpha, beta, gamma elimination reaction. So we'll see E2 is also called as the beta elimination reaction. So we'll see all this is one by reactions. What are alpha reaction, gamma reaction, delta reactions, like that. What are addition reactions? So like our substitution reactions, elimination, it is addition reactions. Same thing, it is an electrophilic addition reactions. So addition of electrophiles. Nucleophilic addition reaction, addition of nucleophile over saturated, unsaturated compounds. And free radical reactions. So again addition by the free radical reaction in the organic reaction is all these are different type of addition reactions. Now let us see in detail what is substitution reaction. Substitution reaction is just like displacement reactions. You know the displacement reactions in which the reaction in which any atom or group of atoms they are attached to carbon in a substrate molecules, and this carbon molecule is replaced by another atoms. When you are replacing the atom or another molecule by another atoms or group of atoms, and then during this reaction what happens, there is no change in the carbon skeleton, means number of carbon skeleton or carbon atoms remain same during the primary carbon chain. So that reaction is called as the organic reaction, yes, substitution reactions. And depending on the mechanism, we have again 3 types already we have seen. So that is free radical, electrophilic, and nucleophilic substitution reactions. So we will see their examples to understand this concept. This is free radical reactions. So in the free radical reactions, normally it takes in gas phase or non-polar solvents. Already we have taken another class in intermediates. You can go in that session to understand the free radical reactions. This is the methane, and methane when they are reacting with the chlorine gas under UV light. So this will go substitution reactions at the CH3Cl, one hydrogen substituted by this 1Cl. Then again if you give the Cl2, so again one hydrogen again replaced by the Cl. So you will get a CH2Cl, HCl is removed, and again one hydrogen is substituted. So again one hydrogen is substituted by the Cl, so you will get CaCl3 is chloroform. Again if you get the Cl2, so again this last hydrogen is replaced by the Cl, you will get CCl. But means all hydrogen is substituted by the Cl, so finally you will get the product CCl4. So like this is one reaction. Second is Cl2. You can see it can react with the one primary carbon or secondary carbon, so we will get the two products. This is also a type of free radical reactions. We are not going to see the mechanism. Mechanism will see the proper chapter. What is the example that we are going to see only? Cl2, suppose this is the methyl butane, 2-methyl butane. So in that case, is the Cl can attach on 1 carbon, 2 carbon, 3 carbon and 4 carbon. So we will be having the mixture of 4 products. So all these are example of free radical substitution reaction. If you take here cyclohexanes, you will get the your chlorocyclohexane. So this is the example of free radical reactions. Now next is electrophilic substitution reactions. So if you see this electrophilic substitution reactions, it is again two types. Acid that is based on order. One is your order of the reaction. This is your electrophilic substitution reaction 1. It is unimolecular reactions, substitution reactions, and second is Ac2C2. So this is your Ac2. This is your bimolecular reaction. So normally Ac1 reaction, unimolecular electrophilic substitution, is very rare, and but the electrophilic substitution reaction Ac2 is bimolecular, is very common, is there. So common means all these are examples of actually Ac2 reaction, that is the electrophilic substitution reactions which is bimolecular. All the examples which I am mentioning down. This is your benzene rings, and this is the your nitric acid, concentrated nitric acid in presence of H2SO4. So this hydrogen is again replaced by the NO2 and water released. So from here OH and hydrogen, OH from the nitric acid and hydrogen from here will form water, and NO2 will form nitrobenzene. So we will see the mechanism later on. So this is toluene. Toluene is reacting with Cl2. So if there is two reactions, one is FeCl3. If you take the dark conditions, so Cl from here it will attack on the ortho position and para position. So on ortho and para position, so this is electrophilic substitution. But if you take the sunlight, so this will undergo free radical reactions. Already I discussed before. This is your allylic, allyl, or you can say your propene. So propene Br2 under 500 degrees Celsius, this will undergo electrophilic substitution reaction. So this will act as a this CH3 will be acting as your carbocation, and it is substituted by the Br2 like a electrophilic. So Br will act as a electrophile. So you will get the HBr. So this Br is your negative, and this Br is your this Br also negative. So you will get this one. Okay. So you will get the Br2 is filled in both the sides. So like this one. Similarly, this is your benzoyl chloride and benzene, and in presence of AlCl3. So this Cl is removed, this Cl is positive, and this will attack on this carbon, right? And after carbon, this will get, you will get this type product, and finally AlCl4 and plus H plus. So H plus and Cl will give you finally HCl gas. So this is also your electrophilic substitution reaction. So if you take this one, this is the 1-chloro-2-methyl propane. So under AlCl3, so Cl3 will make first complex with the Cl, and this is become positive charge, and finally if you react with any reagent, so this will attack on this one. So this is also a electrophilic substitution reactions, and you will get these two products. So all these are electrophilic substitution in which the electrophile is substituted. So all these are electrophiles, like a Br electrophile, this CO is electrophile, this is Cl is electrophile. So all the electrophile, they are substituted on this substrate to give the product. Now next our reaction of substitution is substitution by the nucleophile. So I have said like it has different types. One is SN1, next is your SN2 and SN2 prime, and this is your aromatic nucleophilic substitution, SNI, internal nucleophilic substitution, and neighboring group participation. So we will see one by one details. Let us take first SN2 reactions. So SN2 reaction is nothing but the single step reaction, or we can say concerted reaction. What is concerted means? What is the meaning of concerted reactions? Concerted reaction means the bond breaking and bond making, both phenomena is happening at the same time. How? So let us see. So this is a nucleophile CH3CO. So O is negative charge is there, so definitely it's a nucleophile, and substrate molecule is CH3Br. So this nucleophile will attack on this carbon, and Br goes out. So this both phenomena happens in one step. Okay, this is the backside attacks, and one step. So after one step you will get the product, and Br will leave from the whole reaction as a living group. So so we can say this whole rate of reaction is proportional to the two product. One is a substrate, second is nucleophile. So the whole rate of organic reaction is depending on this concentration of these two products. So this is also called as a second order reaction. So how it is happening? So the nucleophile, and let's take this carbon, and this CX is there, and this is your minus charge. So what will happen? Halogens are more electron, the more electronegative, or its electronegativity is very high. So when it will cause here always a permanent inductive effect. So this is your negative charge, and this is a positive charge. So this is halogen is negative charge and it's positive charge. So definitely the nucleophile will try to attack on this electrophilic carbon because it is positive charge. So it will come from the back side, it can come from the front side. So when it comes from the back side, so this is your transition state. So when it's coming, so it is forming a bond with this carbon. This carbon, these are the bond is forming. And simultaneously, since carbon cannot make 5 bonds, you can say after bond forming, how many bonds are there? 1, 2, 3, 4, 5. There are 5 bonds are there. So okay, since the bond between carbon halogens will make a polarity, so the bond will decrease slowly. It will decrease, and why decrease? Because this bond is also very weak and long, and this bond become with the nucleophile is strong, and when it come close to each other, and this will go slowly outside, and it become a stable your living group. So this is a living group. So halogens is acting as a living group in negative charge. This is most stable, and you will get the product, and this product is inverted. It's not just product will be inverted. So we call as a inversion of configuration, means this product is always 100% inverted product. This is the whole mechanism for SN2 reaction. We'll take some examples. CH3O your Na, so this is your very good nucleophile, and it will replace the Br to form from the back side CH3O, and you will get the NaBr. Similarly, in this reactions, you can see this is Br and Cn will attack. So you can see this Br is going down. Sorry, Cn is going down like this one. So the conversion has been inverted, and Br is out. If you take this phasor projection diagram, so Cl is here. So when you attack by the sodium, this is your thiol. So it is attacking from this side. So this configuration only disturbs. You can see this is Cl. So instead of Cl, you can see the SH and hydrogen is configured invertedly, and Cl is you're out. Similarly, we take this also CH3 PHOT. So this tosylate. Tosylate is also very good living group. So when acetate ion is attacking, so you can see the configurations. It is changed. So pH hydrogen is coming this side. You can see hydrogen this side, pH is opposite side, and OT is replaced by the acetate over here, and tosylate ion is out. Similarly, here Br is attacking with the OH, so OH is replaced by the OH. Br is very good living group, so that is out. Similarly, here is iodopropane. So in case of methoxide, so in the solvent DMSO is a protic solvent. So under this solvent, so iodine is removed, and this will be replaced by the OCH3 from the back side, and we will get the product. So all these are SN2 reactions. Now here we will compare this whole reaction in terms of energy. So I have drawn the energy profile of this SN2 reaction also. So this is the mechanism already we have discussed. This transition state, this is the initial reaction and finally product. So if you see in terms of this diagram also, this is the energy profile of nucleophile, and substrate is there, reactant is there. Their energy is this reaction, and after reaching a transition state, you can see this reaction. This reaction is unstable state, transition state, and you should know very clearly what is transition. Transition state is unstable, and this state we cannot isolate experimentally. So it is internally happening, right? This is internally happening, and this is the maximum energy of this whole reaction, at which the formation of bond and breaking of the bond both take place simultaneously. This bond is slowly breaking, and this bond is slowly forming at the same time. Both are happening same time. So after that, what will happen? The X will goes out. So this is acting in living groups, and you will get the inverted configurations as a final product. So we can say energy of the product is very less. So this we can say this reaction is exothermic reactions. I hope you have understood. Now we'll see some examples for SN2 reactions, like this alkyl halides. Normally this reaction is happening in the halogen groups mostly. So if you take any alkyl halides and if you give aqueous potassium hydroxide, you will get alcohol, ROH. So X is replaced by OH. If you take RONA, so you will get your So OR, so X is replaced by the OR, so it becomes your ether. Similarly, RSNA, so you will get your RSAR, this is your thioether. If you take NaSH or KSH, you will get RSH, RSH is your thiol or mercaptan. If you take CN and CN, potassium cyanide or sodium cyanide, and let me inform you, these are the ionic compounds, so X is replaced by the CN. CN will attack with the R, so this becomes your nitrile. If you take azide, sodium azide, so and this X will be replaced by the azide. And next is RCCNA, so it becomes your so N is replaced, so C is attacked, so it is increasing the carbon. This you can say the carbon is increased. You can say here increase of carbon. So in this case, carbon chain is increased. Okay. Now in this case, RX by RCO, so ROCOR. If you take nitrite and NO2, so it is also ionic compound solvent. If you take DMF, so you will get here ONO, so you will get or NO2. There are two products is there. So if you take ionic or both possible, this is also possible. So this will be your, if it is ionic product, so this will be your minor product and this will be your major product. So if you take the ionic compound, is major product. If it is reacting with the O, so you will get the ionic product. So there are two products is formed with the help of NO2. Now next is the Grignard reagent, so you will get your RX. So again the carbon is increased. These are the way to increase the carbon. If you take RLi, so it will form the RR, means alkane molecules are formed. If you take R2COLi, so you will get the again alkane molecules. If you take lithium aluminum hydride, so hydride is replaced by the your halogen, so you will get RH and X is acting as living groups. And if you use your silver cyanide is covalent compound, so you will get the RNC as a major product. And if you take silver nitrite, so you will get the RNO2 as a major product. RNO2 means actually these two are major products. You can see here this is silver cyanide, and when reacting with the RX, so nitrogen have a lone pair. Lone pair will attack on the R, so you will get the AgCN and next is R. So AgCN and R, NR, this is transition state, and finally Ag is removed, so you will get the RNC. So RNC is your finally your isocyanide. So you will form isocyanide and silver halide is a precipitate. Similarly, this is the AgNO2 is a covalent compound. So there is a covalent bond between oxygen and silver. So lone pair of nitrogen will attack on the RX. Right, lone pair attack on the RX. So you will get here. So lone pair will attack on the R. So you will get the RN2. So you will get silver nitrate and silver halide. So definitely, so there are two difference. One is your one you have heard is this one is there. If you remember, sodium nitrite. So in this case, what happens? Oxygen will attack on the nitrogen, so you will get the RNO and you will get the RNO2. So definitely this will be your major product. So make it correction. This will be your major product and this will be your minor product. Okay, this is the correction, major and minor product. And this is in case of silver nitrates, you will get the ONO is as a major product and NO2 as a NO2 as a major product and ONO as a minor product. So this is just reverse of sodium nitrate and silver nitrate. Similarly, if you take the dry silver oxides, so you will get the ROR and silver oxide, and if you take the moist silver oxides, you will get the alcohol, ROH and silver halides. So moist silver oxide, they are replacing the OH from the silver hydroxide, so you will get the ROH, and here they are it will undergo, so you're replacing the silver as halides, and there is 2 RX is used. Okay, and next one oxygen is OR is from the 2 halogens RX, it will form the ether. So this is the SN2 reactions and you will get this product. So these are the finally reactions of the SN2 reactions, examples of SN2 reactions.